Algorithms are biased. You know algorithms are biased. And I want to point out that sometimes algorithms are biased by design, or at least the biases are well known. Oh, I'm sorry, there's one other thing that I should have mentioned. You have a schedule. The only things you can rely on in the schedule are the start times of when lectures are starting in the morning and when they start in the afternoon. We're going to approximate the schedule, but it won't be exact. Okay. So sometimes algorithms are biased by design. So this is making reference here to the medical school residency match program. Does anybody not know what that is? Great. Yes. Okay. So when people finish with medical school, they need to they want to get residencies, and so what they do is they order the programs. They submit their preference order of the programs. The medical schools, the residency programs, present orderings of the candidates. And then an attempt is made, an algorithm is run, to match up candidates with programs in a stable way so that no pair of residency and person will run away and mess up the remaining orderings. So they use a particular algorithm or a variant of the Gale-Shapley algorithm. Now, there are two roles in this algorithm. There are the people who are proposing, and there are the people who are, there are the people who are proposing, and there are people who are receiving the proposals. So if you were thinking about this as marriage, that would be how it's often referred to in the literature. But the role of which guys get to be the proposers is a policy decision. So it turns out that the algorithm is optimal for the proposers and pessimal for the ones receiving the proposals. And so you can run it in a way that is optimal for the programs, the residency programs, or you could run it in a way that is optimal for the residents who are looking for jobs. Initially, it was always done in a program proposing fashion. And that changed in 1997 in response to, and I'm quoting from the article, a crisis of confidence about whether the matching algorithm was unreasonably favorable to employers at the expense of applicants. So here's a situation where we have an algorithm, it's biased in favor of one group, it's completely known what the biases are, and then a decision is made. Okay. That's not the situation that we're going to be that we're going to be confronting in the rest of this course. So in the rest of this summer program, we're going to be focusing on two kinds of problems in machine learning. So the creation of binary classification algorithms, where we're going to try to classify each person as either positive or negative. Yes, get the loan. Yes, get admitted, whatever. And also a more continuous version, the scoring functions, where to each person we're going to assign a number between 0 and 1. These numbers are often interpreted as probabilities, as in what is the probability that this person will repay a loan. That's extremely problematic, so if you're starting to scream about what is the probability space, you're totally right. We'll get back to that, but nonetheless, scoring functions exist and they're used all the time. Okay. Good. So in the literature on the theory of algorithmic fairness, there initially were two broad groups of concepts or notions of fairness. Group fairness, group fairness and individual fairness. Okay? This thing is not set up well for me to read my own notes, unfortunately. Okay. So group fairness conditions are statistical requirements, typically, about the way in which two different demographic groups, typically disjoint demographic groups, are treated, or multiple demographic groups will be treated. So here are some examples. Statistical parity says that the demographics of accepted students should be the same as the demographics of your population. That would be for a classification algorithm. So if you live in a country which happens to have only 48% women, then 48.7% of the students in college, admitted to college, should be women. Now, in a scoring function, you might have something like balance for the positive class. What this says is that in this kind of definition, there's an assumption that each individual is either positive or negative inherently. They have an internal truth. And now a scoring function is applied. And balance for the positive class says, if you look at the people whose internal truth is positive, is 1, and you look at the average score for a positive member of group A, and you look at the average score for positive members of group B, then those two should be the same. Balance for the positive class. Now, studying this, we felt that group fairness notions fail under scrutiny. So here are some of the reasons why. Imagine that you're an advertiser and you are required to advertise equally to 2 different communities. One community has many vegetarians, and the other community has very few vegetarians. You have a steakhouse. You also don't like this heavy vegetarian group. So when you advertise to the members of this group, instead of advertising to random members of this group, what you do is you seek out the vegetarians in the group, and you only send the ads to the vegetarians in the group. So numerically, you may be satisfying the statistical parity requirement, but it missed the point entirely, right? The people that you're advertising to are not going to be the ones who are going to come to your steakhouse, and so while you have seemingly satisfied the requirement, you really haven't been fair. Another possibility, think about job applications, is that you have a minority community, and you only make offers to, or choose to interview, somehow the more assimilated members of the community. So the members of the minority that sort of look more like the majority, dress more like the majority, for example. Okay. We'll also see that this morning that sort of testing group requirements, group fairness requirements, is surprisingly difficult. And we'll give some examples of how what seem to be very, very natural tests just really are going awry. For me personally, the nail in the coffin for any kind of reliance on group fairness conditions is that there are certain extremely natural desiderata for group fairness. And small sets of these turn out to be mutually incompatible. So natural desiderata can be mutually exclusive, and you can't have an algorithm that simultaneously even satisfies some particular 3 of them that we'll look at, but those 3 are just an example. There are other triples you could find. Okay. And another question that we will return to probably on the 3rd day is when you think about trying to be fair with respect to a collection of groups, very important is the question of which groups do you consider? What does it take to be considered, taken into account in one of these settings? Okay? Good. Now, we will come back to these and give a little bit more details. Yeah, there was a question? Oh, by the way, I'm hard of hearing, so you have to really be loud when you ask the question.
Can you go back to the previous slide?
I think so. This one?
Yeah, could you repeat the second point again, the very different distribution?
Could you repeat the question?
Could you talk a bit more about the second point, very different distributions, reward minority that reflect majority?
Could I say more about that? Yeah. Sure. So, good. Just clarify one thing. What aspect of it would you like me to comment on?
I actually didn't understand what the point was. Could you just repeat what?
You didn't understand the point. So
Oh, you didn't understand the point. Okay, fine. So let's think about golfing. When I was growing up, golfing was very expensive. There weren't a whole lot of municipal golf courses. So you maybe would look on the CV and see, did this person report enjoying golf as a hobby? And only decide to interview for your fancy law firm people who played golf. Or you might do it based on hairstyles. Okay, so typically very important issue in the African American community. You might say, well, we're only going to interview people who have straightened their hair or whatever. People who literally look like or dress like. And this is surely a form of discrimination. Is it clear now? Good.
just to elaborate, so the concern, I mean, beyond what Cynthia said, is that you are interviewing or hiring perhaps the correct proportion of individuals from a protected group, but you're not hiring the right ones, not really the ones that have merit, for example. Rather, you're hiring the ones who are most assimilated to the majority or something like that, and that's a serious fairness concern.
So you're saying that you use rules to cherry pick the distribution?
Yeah, you could cherry pick if that's what you said, right. And this is the same thing, by the way, with the steak ads for the vegetarians. So maybe an anti-Hindu steakhouse would be such an example. Right. Okay. There are other nasty things that happen with cherry picking, and we'll see some examples of those as well. Okay, so, yes?
So is it not the same as the very last point you made about which groups?
It's not entirely the same because the which groups actually allows for a question of being much, much more subtle, and it's still difficult. But so the objection here is that in some sense it's too facile a checkbox. And you need to actually look at the semantics of what's being done and not just say, yes, we are interviewing black people and white people and so on. Right. But you are right that it does boil down to some extent to groups. Yeah. Okay, so we will come back to group fairness, but nonetheless, this alternative, that a branch of work, is on individual fairness. And the intuition for individual fairness is that people who are similar with respect to a given classification or scoring task should be treated similarly. So this is a very simple description, and it's also deceptively simple. So first of all, it does clarify that we're not talking about people being similar in general. We're saying, you want to advertise a book, you should look for people who have similar tastes in their reading. They may use wildly different hair products or enjoy completely different recreational activities other than reading. So it's a very task-specific notion. So how is that captured? That's actually going to be captured with a Lipschitz condition. I'm not telling you how we get our hands on this notion of who is similar to whom, but let me see. Can I get a pointer? Yes. All right, great. So this is a task-specific distance between X and Z, and our algorithms may be deterministic, but they might also be randomized. And if they are randomized, they'll give rise to probability distributions. And the probability distribution on outcomes that is assigned to individual X is very likely to be different than the probability distribution on outcomes assigned to individual Z. But we want to constrain this difference. So for people who are not at all similar, as far as this particular task is concerned, no constraints. But for people who are very similar, yes, there are constraints. Now, that similarly situated people should be treated similarly has a very, very strong legal foundation. But of course, we still have this problem of who should be considered similar to whom. And this problem is not going to go away. We do not have a magic wand. We'll talk about it, and we'll talk about some things that can be done, but there is no magic wand. Now, I think that because of the daunting task of getting our hands on the metric, this line of investigation was kind of quiet for a while until about 2018 and 2019. So Guy will be talking to you about those results, but there was there's this particularly tantalizing breakthrough, in my view, due to Cristina Ilvento, where she imagines that there is a human arbiter who has a pretty good intuitive understanding of who is similar to whom, or the distances between people, the extent of dissimilarity between people. But such a person might not be able to formulate this intuition into a rule. So then the question is, if you have access to such a person as an oracle, how can you come up with some good approximation to this distance without asking all n-squared queries of the oracle and completely exhausting her? And Ilvento's work combines three different insights from some of them, sorry. So here are three insights. First of all, distances from a single representative element, and the word representative is in quotes because there's no semantics to it. We just pick someone and say, hey, we're going to call you a representative, and now let's see what happens. So distances from a single representative element can produce useful approximations to the true metric. But you could have a situation like this. So here my representative is A, and we have H and C who are equidistant from A. But if A says the distance between me and H is 0.6 and the distance between me and C is 0.6, it doesn't mean that the distance between H and C is 0. We might have something like this, or C might be entirely on the other side of A. So we need a kind of parallax. We're looking just through one, and we need one other angle, and that's given by adding a few other representatives. And then there's work, she has results on extending to unseen elements using some simple assumptions. And I think you're going to be covering some of that, right, Guy? Great. Okay. So I've highlighted that getting our hands on the metric is it's challenging, and it's not entirely handled by the existing technology. Maybe you, after this course, will come up with ways of advancing that research agenda. However, Guy and I and Christina and Pragya Sura have a conjecture, and we call this the metric conjecture. And intuitively, what it says is that if you have a system that everybody really feels is fair, then there's a way of extracting from this system an approximation to this metric. So by interacting with it and seeing whether it's deemed fair or unfair, you can build a conjecture, you can build a metric, and we have some work on that. So another problem, when we come to the question of scoring functions, are what do these things mean? So I call this literally the defining problem of artificial intelligence. Artificial AI is supposed to give you scores that are interpreted as probabilities. What does it mean? So, for example, what's the probability, what does it mean to talk about the probability that it will rain tomorrow? Probability over what probability space? What is your experiment? Or what's the probability that individual X, not a random person or whatever, but this specific individual is going to repay the loan? We can't give the loan, run history forward, see if X repays, rewind history, give the loan again, run the experiment again, and so on. We can't do this to build up some kind of frequentist notion of probability. We don't have that. We can't play with history that way. So what should this possibly mean? Or, here's a tumor, here's what we know about it, what the various locations in the DNA, what the SNPs are, what's the probability that this tumor is going to metastasize under a given course of treatment. And the bottleneck here, of course, is we don't know not just that we don't know, but, people who study statistics and probability haven't a good consensus on what does it mean to talk about the probability of a non-repeatable event. So if we don't have that, then, and if algorithms are building scoring functions, how do we say what should be the goal even of the ideal scoring function? What properties should it have if we can't say what a probability is? So it's a very severe definitional problem, and it has to be addressed. And now I'm going to beat this a little bit harder because I want to make a different point, and I'm going to use this example to help me. So let's go back to the tumor example. So here is the tumor, and let's consider a study that was done of tumors. And what I've done here is I've listed, this is the DNA, and I've got various SNPs. Does anybody not know what a SNP is? Good. So your DNA and my DNA are almost identical. There are going to be a couple of places in which they differ. And in fact, if you look at the DNA of everybody in this room, on most locations, everybody will have exactly the same values. Value meaning A, C, G, or T. And of course, we're not really single-strand DNA people, we're double-strand DNA people, but that's just a confusion. So there are certain locations in which, in the human population, there is large variation. Maybe 3% or 5% of the people, instead of having a C, will have a G. So the majority of the people have a C, but a significant minority has the other value. And similarly for an A and T pair. So those are called SNPs, and it stands for single nucleotide polymorphism. So the nucleotides are A, C, G, and T, and polymorphism means that it takes more than one form. So a lot of genome-wide association studies will look at SNPs of healthy people and the same SNPs for the people who have been diagnosed with an illness, and they will look for places in which there's a large variation between the values that the healthy population has and the values that the diagnosed population has, looking for sort of the smoking SNP, the places in the DNA that seem to be correlated with the illness. Okay. So maybe we've done one study, maybe there are multiple studies, but in the first study, maybe the study looked at these locations in the DNA, because there are a couple million SNPs, and most studies don't consider all of them. And so maybe, and these numbers are totally made up, but maybe if we look at tumors that look like this one in the red locations, 0.7% of them metastasize under the given course of treatment. But maybe there's another study which looked at these blue locations instead of the red ones. And in the blue locations, 40% of those that look like this tumor metastasize under the given course of treatment. So of course we don't know what is the truth for the tumor. Is it worse because it's in this intersection set? Is it better than 70? And is it an average? We don't know. The point that I want to drive home with this example is that the representation of our data to our algorithms matters a lot. If I represent tumors by these red locations, and I do a study, and I train an algorithm to make predictions, and then I take this particular tumor and I look just at the red locations and I feed them into the resulting algorithm, we will get one outcome. If instead, when we trained, we looked only at the blue locations, and we built a predictor based on the blue locations, and then we take we represent this tumor to the algorithm looking at the blue locations, we'll get a very different answer. So representation is crucial, and when you think about it, it starts to perhaps become clear that the way in which you represent people to algorithms, both for training and then, of course, for classification and scoring, is a vector for the introduction of bias. And we will see some examples of that. But the key point here is different representations can give you very different outcomes. So keep in mind then that algorithms don't operate on individuals. They operate on some representation of individuals. And there is some abstract representation mapping that takes the individual and presents this individual in sort of redacted form as a reduction to the training algorithm and to the classification or scoring algorithm. And we're always talking about representations, whether we remember to say so or not. The algorithm cannot operate on what it does not see. Okay, now in general, when you have this sort of high dimensional thing being mapped to a lower dimensional thing, because of course the representation won't have everything, you might have collisions. You might have distinct individuals being mapped to the same point in representation space. We're not going to make such an assumption. In any of the things that we talk about, we will never assume that there are collisions. The presence of collisions is not going to hurt us, but we're not going to assume that this is happening. If you have collisions, you can try to come up with frequentist notions of individual probabilities, for example. But we won't have access to that. Okay, so why are algorithms unfair? You've probably read a lot of things in the popular press about this. They're all true, and I want to just review a few examples or points. Oh, does anyone know who this is? Somebody in the back, loudly? That's right, it's Joy Buolamwini, and what's she demonstrating here? She's demonstrating that a facial tracking system fails to detect her face until she puts a white mask in front of it. So, why are algorithms unfair? One reason that is often listed is unrepresentative training data. So you don't have enough, say, black faces in or faces from this group or that group in your data set. Now, what did I want to say? There was something I wanted to say about that. No, it'll come back. All right. Suppose you're trying to train an algorithm to decide admissions to a university, so you decide to train it on past admissions data. Well, if the past admissions data were biased, then, as you all probably realize, your machine learning algorithm will imbibe these biases and will then start to produce biased decisions on its own. Now, this one is really important. And it goes back a bit, it goes back also to the question of representation as a vector for bias. So think about college applications and think about a student who has 0 AP classes on her application. So what are you supposed to make of such a thing? If the student went to a high school that was wealthy and had lots and lots of AP classes offered, and the student did not take any, then maybe there are some semantics to this. Maybe it says that the student doesn't welcome certain kinds of challenges, or whatever. I don't want to get into that. If the student went to a school that was impoverished and has very, very few, or maybe even 0 AP classes offered, then there is no information to be gleaned from the fact that this individual didn't take an AP class because there was none to take. So the feature of how many AP classes, the feature in the representation, that is expressive for one group of people, and it is not expressive for another group of people. So I'm calling this differentially expressive. Doesn't have the same expressiveness in different groups. Another example from this is from the Allegheny Family Screening Tool, which is a forecasting algorithm that's deployed by the Allegheny County Office of Children, Youth, and Families to decide when they get a call about a possible child abuse situation, whether, to use their terminology, they screen that call in for further investigation, or they screen it out and decide not to investigate further. So, suppose that the family being called about is wealthy. Then there's no information, say, about what kind of drug treatment or alcoholism treatment programs the parents of the child may have been involved in, because they're not a matter of public record, they were paid for privately. But if it is the family if it is a poor family, then that information is available because those were paid for by Medicaid and the state has records. So you have, again, differentially expressive features. They're saying much more from one group than about a different group. Another issue has to do with what we call outcome proxies. What we care about is whether the child is abused or not abused, or whether the person is going to commit a violent crime or not. What we have in the data is something different. For the child abuse situation, what we have in the data is whether there was a second call. That's it. So if the, neighbor doesn't like you and decides to make a bunch of calls about you, then you get this record of having abused your child because there's all this follow-up stuff. And of course, if you're densely packed, you may be more likely to have such a neighbor. For violence, we don't or committing further crimes, we don't really know who committed further crimes. What we know is who was rearrested. And if you are policing more heavily in one area than another, it says different things. Your rearrest records say different things. Okay. So these are just some of the reasons that algorithms are unfair. And I remember what I wanted to say about at the beginning, about the unrepresentative training data. One of the things that I learned relatively recently from a photographer is that essentially lenses have been optimized. The design of lenses has been optimized for white faces. And so even the translation from physical to the digital story is already being distorted right then and there, even before you go any further with algorithms and their labels and so on. Okay. Oh, and there's a wonderful, wonderful lecture that I can find a pointer to for anybody who's interested, which talks about how radio was optimized for men's voices. And decisions were made about, how much bandwidth was, I don't remember the physics anymore, that basically penalized women's voices and made them sound more shrill. So the name of the lecture is Shrill. Okay. So these are some of the issues that we're trying to address. And our approach was to sort of fall back on this wonderful paradigm that was developed and deployed successfully. It was developed in cryptography, very successfully deployed in privacy-preserving data analysis, and it goes like this. First of all, you have to define what it means. You have to settle on definitions, because without definitions, you literally don't know what you're talking about. So what does it mean for an algorithm to be fair? And it's fine to put a modifier on that. What does it mean for an algorithm to be this kind of fair or that kind of fair? But you need something mathematical that you can get your hands on. One thing that helps in trying to come up with such a definition, or ruling out candidate definitions, is to design what we call a catalog of evils. If you look at, say, what is the definition of a signature scheme, or what is the definition of encryption, a lot of times what's being described is what it is you are trying to defend against. In a signature scheme, you're trying to defend against forgery. In an encryption scheme, you're trying to defend possibly against an eavesdropper being able to figure out what's being said, or sometimes you want more powerful, you have more powerful requirements. So you build a catalog of evils. It's not necessarily going to be complete. You do your best, and then you evaluate candidate algorithms from them. If you can come up with, in light of them, if you can come up with an algorithm that wards off this particular family of evils, good. Maybe you'll have to do more later, but it's a starting point. Now, building the catalog of evils is hard. I'm not saying, and you don't know when you're done, and blah, 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 blah. And this is kind of where the human part comes in. You have to think, what is it that is unfair that you want to rule out? And one of the reasons that algorithmic fairness is such an unwieldy field is that humans, people in this room even, probably don't agree on exactly what's fair and what's not fair. So you're going to have to either find an abstract way of capturing fairness constraints, as we did with the metric, or make some choices and place your bets. Okay. Once you have your definition, you want to construct algorithms that are fair according to this definition, whatever it is. And there has been some success doing that, and we'll talk about some of that. And then the real world is not the same. In vivo is not the same as in vitro. In vitro, you've got like your one little example and you want to see what happens. In vivo, things are happening all the time. Nobody wants to encrypt one message. They want to encrypt a zillion messages, all of the traffic on the web using HTTPS. You don't want to have just one episode of classification. You want to be able to do it many times. You want to score many people, many different systems. So you want to somehow or other prove that systems that are built from fair individual pieces will, when taken together, give you fairness in toto. And oddly and astonishingly, often this is not the case, and we'll see some examples. But this is the paradigm. Okay. So let's start then with a couple of fairness evils, things that we want to defend against. And it might be useful to know that when we first did this, we were thinking about an advertising platform. So we were imagining a scenario where an advertising platform has huge amounts of information about you because they've been tracking you and watching you. And we were sort of imagining even that anything that this thing was trying to predict or whatever, it had enough information to do. That's not always going to be the case, but I just want to cue you in a little bit on how we were thinking at the time. Okay, so first, explicit discrimination. So in general, I'm going to use two groups, S and T. Sometimes I will refer to them as people who like to eat food that is flavored with sage versus eating food that is flavored with thyme. You can think of these as racial groups. You can think of these as gender groups. You can think of these as sex groups. You can think of these as people who grew up having access to abortion and people who grew up not having access to abortion. So there's explicit discrimination, which will explicitly test for membership in a set and give a less desirable outcome to members of S. Another possibility is redlining. Who is not familiar with redlining? Okay. Redlining is a well-known form of discrimination, which is based on what I would call a redundant encoding. Information about your income or your race may be kind of embedded in your zip code. And let me show you. This is a map. I think it was a map from Philadelphia. Can anybody correct me on that? What does it have? It has neighborhoods classified according to wealth. So redlining is the practice of arbitrarily denying or limiting financial services to specific neighborhoods, generally because its residents are people of color or are poor. And so I don't know if you can see this, and my eyesight has long since given up, but yellow corresponds to declining, red seems to say hazardous, and so on. And the redlining is saying these are bad neighborhoods and you do not wish to give loans for homes in those neighborhoods. And the map, this was the map, and it was red, and that was where the term redlining came from. But the general concept is that information about you is not, sensitive information about you is often not just held in one particular field, but it's kind of spread holographically in all of your information. In all of your information. So the fact that I am a woman might be clear. Remember, we were thinking about the advertising and platform. Might be clear in terms of what kinds of clothes that I buy, what kind of hair products I buy, what sorts of shoes I buy, possibly some of my reading interests, and so on. And so even if it doesn't explicitly say female, it's certainly discernible. It's redundantly encoded in the rest of my data. This was actually a really recent map showing the effects of redlining. So this is actually a map of pollution, and where this is the nitrous oxide pollution map in 2010, and it turns out to be very tightly correlated to redlined areas in the Bay Area. Okay, another possible evil would be cutting off business with an S-heavy segment of the population. So we saw that with the steak ads for vegetarians, where S might be the Hindus. Okay, then another possibility would be deliberately choosing the wrong members of S, not as in the previous bullet, but maybe in order to build a negative track record for a group. Oh, we tried having students from this group, but they didn't work out. And so again, this is a question of sort of superficially choosing people from S, but maybe you're choosing random people from S rather than choosing qualified people from S. And then you build up a bad track record for S, justifying future discrimination. Another possibility, a real possibility as it turned out, is yes, we have to interview a certain number of minority candidates, so we literally choose the wrong minority candidates to interview, and then they don't get the jobs. But hey, we tried, we interviewed. So this is real. And another is what I call reverse tokenism. So this concept arose in the context of imagining what might be a convincing refutation to the claim, the bank denied me a loan because I'm a member of Group S. So one way that the bank can refute this is to exhibit sort of an obviously very qualified person from the majority group T who was denied a loan, and then using this as the counter example. I was denied this before because I'm a member of S. No, look, here's this other person from T who's even more qualified than you, obviously, and we turned that person down as well. The problem is that this token T person is being used as the counter example for lots and lots of different complaints. Okay. I have no idea why this is here. I don't, I think this was for my reverse tokenism example. Okay, great. Now, this is an incomplete catalog. You can surely think of additional ones. Do. Spend time on this. Think of other ways that things can be unfair that you want to defend against. See whether any of the proposed techniques defend against or fail to defend against. Like, do we need to up our game? Okay. So now I want to go back a little bit to the group case. So again, remember, just sort of drilling this in, group fairness properties are statistical requirements, and statistical parity says that demographics of people assigned a positive classification are the same as the demographics of the general population, and similarly for negative classifications. So I want to emphasize that statistical parity might be meaningful when it doesn't occur. If you fail to have statistical parity, that could be a flag that says, look at what's happening here. I'm not saying never think about these things. What I'm saying is that they are incomplete as solution concepts. So for those who don't know, this is Abraham Lincoln, considered one of the great American presidents. He was very poor. So if you're advertising for, I don't know what, something exclusive, sending an ad to Lincoln, he's not going to come. He's not going to be there. Okay. Another example is it's a calibration condition. So this was introduced as a fairness condition in work of Kleinberg, Mullainathan, and Raghavan. And so here we have our two different groups, represented by the herbs, sage, and thyme. And here we're going to be, oh yeah, there was a question?
On the statistical parity slide.
Oh, what's the question about statistical parity?
Do you want me to come closer?
Yeah.
Or I can just check. Okay.
No, come and use them. I'm sorry I can't hear better.
In your definition of statistical parity, you had on there the general population, specifically the general population. And like, I often see that there's kind of this like, the general population versus like maybe the population of interest, like the SNTs that apply to the school, not the SNTs in the world. Can you talk about that? Like, do you always go with the general?
No, you're totally right, and I was giving the general population as an example, and you definitely, there are definitely times when you want to talk about the population that applied. Of course, you have to be careful because you have to make sure that you're making efforts to get a broad applicant group. This comes up, I think, a lot. So think about jobs, and there are laws about how you have to, as an employer, how you have to handle an applicant pool. And now move to LinkedIn, where there are no applicants. There's no applicant pool. There's just, here's the people who are on LinkedIn, and you're going to go fishing within this group. You're going to go searching within this group. So you're absolutely right. These questions arise, and contextually, you have to figure out what's the right one. Any other questions while we are here? So that's good, and do keep asking questions. Okay, so let's see. So here I have people from the groups S and T, and The calibration for a scoring function in this, requiring that my scoring function be calibrated on both S and T is supposed to say, imagine this, imagine that the scoring functions places people in bins, 0.1, 0.2, 0.3, and these are really ranges between 0.1 and 0.2, between 0 and 0.1, and so on. So the scoring function puts people in bins, and calibration says, if you look at all of the people who got a score of V, for any value V in any bin, then this is the correct number in expectation. So among those who were assigned the score 0.3, 30% of them had positive outcomes. Okay? So in this example, I have people in the two different groups, S and T, and let's suppose that both groups are identical in terms of their distribution, and in fact, half of the people in the group, in the SAGE group, have a true value of 0.1, and half of them have a true value of 0.9. And similarly over here in the time group. And then what we do is we assign to everybody in this group the score of 0.5, which is correct on average. It's correct in expectation, because these people are half 0.1s and half 0.9s. For these people, we give the 0.1s the 0.1, and we give the 0.9s the 0.9. That is also calibrated. But something is really not quite fair here. Suppose you combine this with some sort of a threshold of, I'm going to take you as give you a loan if your score is above 0.8. Then nobody here gets a loan, and half the people over here will get a loan. So nothing forces remotely comparable differentiation by the scoring function on your set. Okay. Now, that was for scoring functions. Now let's look at just the classification situation, where you have people who have an inner truth of yes or no, true or 1 or 0, and then they're classified a certain way. Now, here are 3 things that you might want, natural things that you might want. You might want that the false positive rate will be the same across the two different groups. You might also want that the false negative rate should be the same across the groups. And you may also hope that, in contrast to the example I just gave, you have comparable positive predictive value, meaning among these people for whom we say yes, what is the fraction that truly are positive? And the result by Choldachova says that if you have an imperfect classifier, and classifiers will be imperfect, but unless your error rates are 0, no imperfect classifier can simultaneously ensure equal false positive, false negative, and positive predictive values unless the base rates for the two groups are equal. So the base rate is, here are the people in the group, some of them are positive, that's the base rate for that group. So this is pretty important result, and it has a really easy proof. So the relationships between false positive rates, false negative rates, positive predictive values, and base rates are given by this equation. Was there a question?
Yes, sorry. Back to the calibration example, I think I missed something about your counter example with the 0.5, because I thought that if the probability, if an expectation probability that you're being put in the 0.5 bucket, given your group membership is the same, then
No. So
should it be calibrated still? Like that would be calibrated.
So calibration says that among those who were assigned the value V, the same fraction, a V fraction of them are positive. So in the SAGE set, half the people are going to end up being positive. because their rates are 0.1 and 0.9, and we just lumped them all together and called them 0.5 for everybody. So if the truth is that for the people whose truth is 0.1, suppose that really means, I don't know what randomness actually means in this setting, but suppose we did. Suppose that really meant that 1/10 of them were going to have a positive outcome. And for the people whose truth is 0.9, 9/10 of them will have a positive outcome. Okay. So if my group is split evenly, half 0.1s and half 0.9s, then as a whole, the group is going to have half positives and half negatives. As a whole. It'll be the average of those two, because it's an even split and they're... So a value of V, it will be true that about half the people will have a positive outcome among the people who end up getting scored as a half. Their truth is either 0.1 or 0.9, but they were given a score of 0.5. Even more extreme, suppose the truths were 0 and 1. Then we really know that half of the people in that group are positive and half of them are negative. And if we give them all a score of a half, it'll be true that half of those will have positive outcomes.
So maybe it's important that we're not requiring the same fraction of people in S and T to get any particular score.
Right.
No requirement like that. The requirement is just that of the people who get a particular score in S and in T, the score is 0.1, 10% should be 1s, 10% should be 1s, 90, 0, and the same in T. But we're not requiring the same distribution of scores either. That would be more like a statistical theory type of requirement.
That's right.
So this is more of an accuracy requirement, both on S and
Yeah, right. It is an accuracy requirement. I agree. We're going to drive that home with another example shortly. Was there another question? I think you had a question? No? You were making Guy's point. Excellent. Good. Okay. So you know, if you're not sure about this equation, go to the Wikipedia page, the confusion matrix, and plug in the definitions of these quantities, and you'll see this. And this has nothing to do with what group you're in. This is just like a mathematical fact. So it's going to be true both for the members of S and for the members of T. So I can write this equation where everything is now subscripted with S to say that I'm talking about the people in S, and I can write it again subscripted with T to say that I'm talking about the people in T. And then we just say what are the requirements. So we require that these two quantities be equal because we want the same false positive rates in the two groups. And then we require that these two quantities are equal because we require that the positive predictive value be the same for the two groups. And then we require that these are equal because we require the false negative rates to be equal across groups. And with all these equalities, that's going to force PS equal to PT. The base rates will have to be the same. Now I have a quiz. If we introduce a human into this classification process, does this resolve the problem? No, it's just some other algorithm that happens to have a human, but this is a mathematical equality. There's nothing you can do about it. And if we put in a classification god that meets out judgment between good and evil, positive, does it help? No, it doesn't. It's just a mathematical requirement. Okay. Should I stop? This is a time for a break.